So a bit of a sound check. Can you hear me in the back now? Okay, very good. So I come from Ericsson, and I will tell you a little bit about our view on 5G, and then in particular in connection with the industrial applications. And when we started to talk about 5G, we said that it would be ready around 2020. And at that time, it sounded like a far vision, right? So anything is possible in 2020. So it was very visionary and so on. But now it's only 5 years left. So now we have to be a little bit more concrete and sort of think of what we actually do on the next 5 years. And I will talk about that. But I will also go into a little bit the 4G and the 4G evolution, because we think that will be a very important part on the road towards 5G. So I will cover that also. And to start with then, sort of a high-level view on what kind of use cases do we foresee that 5G will cover. And obviously, we would like that 5G will offer sort of a superior user experience for those use cases that 4G can handle today. I'm talking about mobile broadband, video delivery, gaming, etc. But I will not talk so much about that. I will talk about sort of the new use cases that we foresee that 5G will cover, that we see on the right side here. And then we go into industrial applications, machine-type communications, Internet of Things, Industry 4.0, and all that. Looking a little bit about some predictions, starting this year, we are now including sort of connected things in our official forecast from Ericsson. If you want to see more detailed data, you can go into our mobility report that you find on the net, where you have a lot of statistics like this. And sort of we see that there is a very strong growth in connected things. And at the moment, we are estimating that there are around 14 billion connected devices in total. And this will roughly double until 2020, where we see that there will be around 26 billion connected devices. And the growth is not in mobile phones anymore, because we have already given mobile phones to most people in the world. So the penetration is already very high there. So the growth potential is really around this, what we call here, machine-to-machine and consumer electronics, which includes then this Internet of Things domain. So there we will see that there will be 4 times growth in sort of the number of devices there. And as you could probably guess already, the number of fixed phones, that is already decreasing, because people are giving up their fixed phones in favor of mobile phones. And a note on this one, so in order to be classified as a connected device in this forecast, you need to be a sort of a device with some kind of intelligence. So you need to be capable of two-way communication, and you need to have some kind of processor so you can be reconfigured. So you need to be able to act on received messages and so on. So a simple temperature sensor that just sends messages and you can't really configure it or reach it, that is not included in this forecast. So that's one reason why the number is slightly lower than what you might have seen from other sources. And these are the things that we need to connect. And when we talk about machine-type communication, there's obviously an extremely broad range of different kind of devices and things that we can connect. And the requirements are also very diverse. And to create a little bit of order in this, we are normally dividing the devices in 2 categories. We call them massive machine-type communication, when we talk about small, cheap devices that transmit rather little amount of data, but they can have extremely large numbers. And on the other side, we talk about critical MTC for devices that require reliable real-time communication. And the requirements here are very diverse. On the right side, it's high reliability and extremely low latency that matters. And on the left side, it is device cost, battery lifetime. That is the most important criteria. And we will come back a little bit to these 2 classes of devices and what this means for the connectivity. And obviously, these are 2 endpoints on the scale, so there are a lot of applications that fall in between. And it's perfectly possible to that an application is both massive and critical at the same time. So, for example, if you take a connected fire alarm or so, it sort of has the properties of massive MTC in the sense that it transmits very little data, and there could be many of them. But when this message comes, it's very, very critical that it's received correctly. So it's in that sense also critical. And talking about networks for 2020 and talking about 5G networks, we have to realize that this is not only the radio network we are talking about. The radio network is obviously important, but we need much more than that. So we need the whole core network. Today we have a core network with actual core networks nodes, as Misha was talking about. For 5G, we don't foresee that will be the case, that it will be a cloud infrastructure, and what we today know as core network nodes, that will be sort of applications running on top of this cloud infrastructure. And we also need a transport network, we need management functionality and all that. And when we talk about the 5G network, we sort of talk about the whole system here. And on the access part, we see that there can be several accesses connected to this 5G network, to this 5G system. And we think that the LTE evolution will be a very important part of 5G. It will be able to handle a large extent of these 5G use cases. We will foresee that there will be a new air interface that we have called NX, which is then, if you like, the 5G new air interface. But there could also be other accesses that are sort of connected into this 5G system. For example, Wi-Fi. Wi-Fi will obviously exist and will be integrated with the other accesses. There could be also legacy 3GPP systems like 3G or maybe even 2G into this. And we can even connect these short-range technologies like Bluetooth, Zigbee, and so on that will be used in for example, in buildings, for building automation and so on. And those can then be connected to the internet via a gateway, and that gateway can then have a backhaul link that is either NX or LTE. And then they can also be managed and operated in the same network. So when we talk about 5G as a system, we talk about this whole thing. When it comes to supporting industrial applications, we foresee that there will be many industries that needs to coexist in the same network. So we cannot afford to have sort of dedicated networks for each industry segment. So if there will be one network for mobile broadband, one for automotive, one for utilities and so on, that would be too expensive to build and maintain. So what we foresee is that there would be one physical infrastructure which can be divided into what we call network slices, where sort of each network slice can be optimized and configured for the needs of an industry, for a service, and so on. And you see some examples here depicted, and that means that you can optimize. So for example, if you have a latency critical application, you can make sure that your core network functionality is configured to be located very close to your devices to minimize the delay. You can have duplication of functionality if you need very high reliability, for example. And on the other hand, if it's a media service, you most likely need some media caches in the network, and they can be configured in smart places to suit the application and so on. So in this way, we foresee that there will be one network that can sort of handle a large range of industrial use cases. On the physical layer, this doesn't mean that it will be necessarily one physical layer as we showed in the beginning. So the access part can vary depending on the requirements. And in order to run a wireless network, we obviously need spectrum, and we need quite a lot of spectrum to handle the high capacity and bit rates that we foresee. We are talking about several 100 megahertz per operator or per network. And in order to find that spectrum, we need to go up higher in frequencies than what we have today. And it is not known at the moment exactly which frequency bands that will be available for 5G. But we know that we will need to be flexible. We need to be able to operate in both licensed and unlicensed bands, and also apply different spectrum sharing techniques in order to get the performance that we really need. And some of the spectrum will be FTD, some of it will be TDD, so we need to support both. And when we talk about TDD, we foresee that it will be dynamic TDD, much more dynamic than we have in LTE today, for example, where you have a rather fixed static uplink downlink configuration that is quite cumbersome to change. So it needs to be very dynamic. The NX air interface, then we foresee that will be deployed mainly in new spectrum that is not used today, whereas the LTE and the LTE evolution will then continue to evolve and using existing spectrum. And here we will support some of the 5G use cases also. And over time, we can also see that there could be a gradual migration, that the NX air interface also goes into the currently used frequencies. So in the very long term, the NX can then replace LTE. LTE evolution, I already said that there is an or we foresee that LTE will play a very important role in the road towards 5G. And I wanted to show a little bit what's happening here, just to give a flavor that there is quite a lot of things going on also on the LTE side. This is some items that are being discussed for release 14, which is the sort of next release of 3GPP beyond what they are doing right now. And here there will be first latency reductions, meaning that the latency of the air interface is reduced quite significantly compared to today, which will enable some new use cases. Some of these critical MTC use cases, but not all. There will be licensed assisted access enhancements, LLA, and the LLA that is then using LTE in unlicensed bands, so in the Wi-Fi bands, basically. And there is a first version of that being standardized now, so you will be able to use LTE in the Wi-Fi bands, but it has some limitations. For example, it's only downlink, and there has some other limitations as well. But in release 14, we foresee that there will be further enhancements on this to increase the performance further. I also want to mention that there will be support for vehicle-to-X applications, meaning vehicle-to-vehicle, vehicle-to-infrastructure, vehicle-to-pedestrian, and so on. And then we're mainly talking about device-to-device enhancements to make LTE suitable for automotive use cases. So this is just some examples of what is happening in LTE. So, and we think that or we would like that as many of the 5G use cases as possible are handled also in LTE. Then NX. NX is the new air interface that we foresee. And I listed some of the sort of design principles that we foresee that we need for this new air interface. And one of the most important things is that it's flexible, because there is a huge range of scenarios, both when it comes to frequency. For example, you need to be able to handle in the end from 1 to 100 gigahertz of frequency, not necessarily with one physical A configuration, but with the same physical A framework that is then configurable depending on in which frequency band you operate. There's a very large range of use cases that we have talked about a little. And also the deployments vary from very dense indoor deployments to large macro cells, and that also needs to be supported. So the flexibility, scalability is very important, and also the future-proofness. So we need to be able to add new features and support for new use cases along the way. And one example of doing that is to avoid that there are sort of too much control signaling that is sort of needs to be transmitted at certain time and frequency resources that the mobile terminals are expecting to always be there. That is the case in LTE, and that makes it a bit difficult to change the design, because then you cannot anymore support the old legacy devices, because they expect that it will be like this. And if you can minimize that kind of inbuilt mandatory signaling, that makes it easier to add new features along the way. Ultra lean design, that means that you should send as little control signals and reference symbols and so on as possible. One reason for that is that you decrease the interference in the system, but also you reduce the energy consumption of the network nodes, because today the energy consumption in cellular systems is, if you look at the network side, is not really dominated by the energy you spend on transmitting data. It's many times dominated by the energy you spend on just transmitting broadcast information to make it possible for terminals to access the network, especially in low load situations. So I can mention, okay, we need advanced antenna solutions, both massive MIMO when it comes to high peak rates and capacity, and also beamforming to compensate for some of the losses you get when operating at high frequency bands. We foresee that D2D needs to be there from day one, and not sort of something we add later. It needs to be integrated in the design. And we also foresee that the same air interface should be possible to use both for the access link from the terminal to the base station, as well as the backhaul link between base stations. So you need to be able to do backhauling with the same radio interface. So those are some of the design principles in general we foresee for NX. And a little bit on the timing and the standardization, and this may be a little bit of a dry slide, but I think it's good to be aware of the time perspective here. So obviously specifying a new system is a huge undertaking, and it takes several years to complete. At the same time, there is quite a push from some operators, especially in Asia, to have an early commercial deployment. And to solve this dilemma, it has in 3GPP been agreed to make a phased standardization. So there will be a phase one that will target sort of early commercial deployments that will be ready in time to have a commercial deployment somewhere around 2018, just in time for some major sports events in Asian countries. And then there will be a later phase two, which will then contain the whole set of requirements specified by ICUMT. And the ICUMT is the body that really defines that what can be called 5G. So in order for this technology to be classified as a 5G technology, we need to fulfill all the requirements specified by ICUMT. And here we foresee that will happen somewhere around 2020, sort of the first commercial deployments with full capabilities. But the work has already started. So already now there is work ongoing on channel models, and we are starting up now looking into the requirements in the 3GPP community. So that was about the timeline. Then going into a little bit more on this different kind of MTC communication and what that really requires from the network. So massive MTC, that sometimes we call it IoT, and the key properties that you need to improve if you want to support these IoT applications in cellular systems are listed here. So cost is very important, and then sort of it's important already today when you have smartphones and so on. But if you are connecting very cheap devices like a connected toothbrush or so, obviously the sort of price point of the communication module needs to go down significantly to make it feasible to add such a communication module. Battery life, since many of these devices are battery operated, you need to operate very long time on a battery, preferably the whole lifetime of the device. if you put out some sensor in the forest, for example, you can't go there and change batteries, most likely. So we are talking about battery lifetimes in the order of 10 years or more on a single AA battery. And the coverage is important since some of these sensors are located in difficult locations. And the typical example here is smart meters that may be located down in basements in apartment buildings, for example. And if you can't reach them, then it's very expensive to add. Then you need some special repeater or other type of solutions to reach those devices. So the coverage aspect is also very important. Then there are some aspects where the cellular systems already are very good and capable, and security is one example. There is a very good security mechanism inbuilt if you compare with most alternative solutions, and also quality of service support is there, and so on. So there are some things that where cellular is obviously very strong. But these are the things that we foresee needs to be enhanced. And as Misha mentioned earlier, I mean, there are several systems addressing these kind of use cases already in the unlicensed band. So we have the short-range technologies, Bluetooth, Zigbee, etc. And then we have some long-range technologies like Sigfox, on-ramp, LoRa, and so on. And we think that this will play a role also in the future. Especially in sort of inside buildings and so on, it could be suitable to use the short-range technologies in some cases. We think that the long-range technologies in unlicensed bands, they have a role to play now in the short term, but over time, when the sort of interference increases in these unlicensed bands, it will be very difficult to have a good performance with those technologies. So in the long run, we foresee that standardized technologies in the licensed spectrum will be sort of the main technologies for these kind of use cases. And Misha mentioned some example here where one sensor was picking up a signal between Paris and Barcelona, and if that is the case, then it will also pick up all the interference from the devices in that area. And that interference can come from a long row of other systems in this band, including the short-range technologies, which operates partly in the same band. So there's quite crowded spectrum, these ISM bands. But on the licensed spectrum, then it has happened quite a lot the last couple of years. So if we go 2 years back or so, then there was the feeling that cellular systems were not really fully addressing this IoT domain. There was maybe a limited interest by companies to do something about it. Now we have suddenly 3 different tracks in 3GPP addressing more or less the same requirements. So we have 3 tracks, all of them focusing on reducing the device cost, improving the coverage, and improving the battery lifetime. And we think that all of them have a role to play depending on the situation of the operator. So, for example, there is one GSM track, which is called Enhanced Coverage GSM. And that is very suitable for operators that already has a GSM network rolled out. He wants to reuse that infrastructure. He can do a software upgrade in the network, and then boom, he can suddenly support these new features in this whole network. So that is very powerful for those operators that have that situation. On the other hand, if you don't have a GSM network or you want to replace it with LTE, there are 2 LTE tracks at the moment. There is one sort of normal LTE evolution track, if you like, where we have been enhancing LTE to support machine-type communication for several years. I will talk a little bit more on the later slides. The benefits with this is that it has very good capabilities also beyond supporting these very low-end applications. So if you have some machine applications that require a little bit more, like a surveillance camera or something, that can easily be supported as well, since you have the capabilities of LTE. And then there is a completely new track that is called narrowband IoT, which is a narrowband LTE version, the normal LTE track that has 1.4 megahertz bandwidth. This track has an 180 kilohertz bandwidth. So it's a narrowband solution. It will reuse much of LTE design. And the deployment options here are a little bit different. So you can deploy this system in if you have a GSM carrier. You can replace a GSM carrier with a narrowband IoT carrier. You can run it in the guard bands of LTE, or you can use it within your LTE resources and schedule it as part of your sort of total resources you have also for other applications. And we think that all three tracks here have a role to play. They will come. I mean, the bottom track has already started, and some of the solutions have already come out in release 12 that is already ready, whereas the other top two will come in release 13 that will then finish at the end of this year or beginning next year. One concrete example of an application that will need this kind of enhancements is wearables. I mean, there's a massive amount of wearables coming out now in the market, both this multi-purpose like the Apple Watch and this kind of thing where you can download apps, but also more specialized devices. For example, for elderly that want to live at home, you can have a device that checks if you fall down, or if you don't get out of bed, or if you don't come home from your daily walk and things like this. And today, the common approach for the connectivity of these kind of devices is to pair it with either you have a gateway in your home or you pair it with your mobile phone, and by that you have the connectivity. But it would, of course, be much nicer if you could do this directly over cellular, because then you're not dependent on this gateway and this phone. So if you have forgotten your phone at home, it would still work. If you have a sports application, it's sort of much nicer to only have a small watch than your smartphone with you, etc., etc. So there are some benefits of having direct cellular, but then there could be some concerns then. What about the module cost? If you want to put in an LTE chipset today, the cost may be too much to make a feasible business case. And the battery lifetime as well. You don't want to charge this too often, so you need enhancements in the energy consumption also. And what have we then done or are doing to address these properties? So when it comes to the battery lifetime, the key to address the battery lifetime for these kind of applications is not really to optimize the energy that is spent on transmitting data. It's energy that is spent when you're not transmitting data, because these devices generate quite infrequent packet transmissions. And if you want to build an MTC device today for a sensor, for example, that transmits measurements once every hour or something in that order, you still need to follow the paging cycle that was defined for smartphones. And for smartphones, it makes sense to be reachable like every second or every 2 seconds or so. So you cannot configure that to more than 2.5 seconds. So even if you have nothing to transmit or receive, you still need to wake up every 2.5 seconds to check if there is a paging message for you. And this is what drains the battery today if you try to build an sort of optimized machine type device. So very efficient sleep mechanism, that is what gives the largest gains for these kind of applications. And you also need to minimize the signaling as much as possible, because today, even if you have very little data to transmit, just one measurement of a few bytes or so, there is quite a lot of signaling involved to setting up the connection, setting up the security, and all that. So that needs to be improved also. The target here was to reach 10 years battery lifetime. And actually that is then has already been done in release 12. That has been finalized with something we call the power save mode. And what is done is basically that we turn off this paging completely. So if terminal go into a deep sleep state, that is called the power save state, where you cannot page it. And that if the device needs to send some uplink data or at configured intervals, it wakes up, it sends something to the network, and at that point in time, you can reach it if you have something to send in the downlink, but otherwise not. And here you see then what kind of battery lifetimes we can enable with these mechanisms. And of course, the battery lifetime depends on how often you need to transmit data and how often you need to be reachable. But if you can live with reachability of 3 hours and you have something to transmit every 3 hours, we can reach around 19 years here with some assumptions. And these assumptions here are assuming 2 AA batteries and a certain self-discharge there for the battery that assumes a rather good battery, so probably not the one you would have in your drawer. But still, it is possible to build this, and it was not even very difficult. Then the work continues to have similar enhancements also when you have more frequent transmissions. This is really suitable when you have really infrequent transmissions. Modern cost reduction, also here it is work ongoing for LTE to reduce the modern cost quite a lot. And here it is mostly about relaxing the requirements, because so far the simplest LTE device you are allowed to build is actually quite complicated. You need to support a high bit rate. You need to support 2 receiver chains. You need to support a wide bandwidth and so on. And by gradually sort of relaxing these requirements and allowing you to build a low complexity device, we can reduce the complexity down to around 20-25% of what it was for a release 8 LTE chipset. And this brings it on par or even slightly lower than GPRS module. So there's no really sort of advanced technology involved there. And this also means that, so far it has been really a race when it on the chipsets and the communication modules towards more and more powerful communication modules for smartphones. That has been driving the development, and that's also maybe one reason why cellular has not been so suitable for these low-end applications, because they were not at all optimized for that. But now we see these 2 trends. On one hand, we are going to see more and more advanced, high performance chipsets, and on the other hand, we are seeing more and more simple, low-cost devices to support these low-end IoT applications. Okay, so that was then the massive MTC. And some words about the critical MTC then. So here we talk about mainly industrial applications that require low latency, high reliability. We also include the tactile internet in this definition. And here are some examples of industrial use cases that fall in this category. We see quite tough requirements in factory automation, down to even below 1 millisecond. I will talk a little bit more on that. In the automotive arena, there are several use cases that require low latency with high reliability, like collision avoidance, collaborative platooning, and other type of use cases. And that's also a potentially big market, so that has a high interest in the industry today. We heard about the smart grid quite a lot. The tactile internet from Misha, and in the smart grid for utilities, there's also some very challenging use cases when it comes to protection of the infrastructure. So if there's a fault somewhere, you need to shut down part of the network very quickly to avoid damages and so on. So these are some examples. Some more concrete ones. Remote control or remote operation of machines. This goes a little bit in the direction what Misha also showed. This is something we demoed earlier this year in Barcelona. So you could sit in Barcelona in this control station, and then you could then drive this wheel loader that we had in Sweden. And you could feel how that worked. And this was something we did over the LTE network. So it both showed the sort of potential of doing this over cellular, but it also highlighted that the LTE, as we know today, has some limitations when it comes to latency to support this in a good way. And we didn't have the haptic feedback here, but if we would add that, then it would be even more apparent that sort of the latency is not good enough. And this is actually a use case that has quite some attention in the industry. There are several environments where you would like to avoid having personnel on site, like in mines, partly in construction sites, and in oil and gas and so on. So if you can handle tasks remotely, that would be a big benefit. Another example was the factory automation, and if you have a manufacturing equipment that you want to control from a server in a factory, and you act on sensor information, and then you control, for example, a robotic arm or some other manufacturing machinery, the latency requirements gets very strict. And we see examples of fraction of a millisecond with extremely high reliability requirements as well. And these numbers now actually come from the reliability that you would get from a cable, because the cable is what is mostly used today. And so if you would like to replace that cable with a wireless connection, this is the properties you would need. If you would design the whole solution around a wireless connectivity, then it would look slightly different. And I think you have a lot of expertise on that in this room. But these are some examples of applications that require very low latency and high reliability at the same time. And it's really sort of the upper latency bound that we are after. So it's not the average latency that's important. It's the latency that you can guarantee, so that you can support these reliably. And what do we need to do to achieve low latency then? Well, there are mainly sort of the design choices you do. Now I talk about the physical layer on the air interface. So you need to have a very short time structure, much shorter than today. You should avoid retransmissions as much as possible. In some cases, you don't have even time to do a single retransmission. So you need to have it first time right. The coding and modulation need to be adapted for this scenario. So the codings that we used in mobile broadband, for example, which are these high-performing iterative codes like turbo codes and so on, they are not so suitable if you need to have a very short decoding time, and you also have very short packets. So another type of coding would be needed. And also there needs to be new scheduling mechanisms, because currently in cellular systems you need to request resources from the network to the device, and the request, can I please have a resource to transmit, and your network responds, yes you can, please transmit at this time, and this handshaking takes quite a lot of time, and that we need to limit as well. So then we have something we call instant uplink access, for example, where you will remove some of these steps in the scheduling sequence. And reliability, just showing one figure here. So it is quite expensive in terms of radio resources and transmitted power to achieve extremely high reliability on the wireless link. So if you have a rarely fading channel and you are aiming for a reliability of 10 to the power of -5 to the power of -9, you will need a fading margin of roughly 50 to 90 dB. But if you add diversity into this, sort of the needed fading margin goes down significantly. So in this case, if you go from a diversity order going from 5 to diversity order 8, you reduce the needed fading margin down to 18 dB. So diversity will be a key part of the solution. And there are different ways to do that, of course. You could have antenna diversity, you can have frequency diversity, and you can combine this in clever ways by using coding. But it's more difficult to use time diversity due to the timing constraints. So the use of diversity will be key in the design here. And in the whole system solution, of course, you need to look at redundancy of the functionality, and maybe you need to have transmission from multiple nodes and so on in the radio network. Right, so that was a little bit about what we see happening for massive and critical MTC. Then I wanted to say a few words also about the new initiative we have that is called 5G for Europe, which is something that Ericsson has launched recently. There was a press release some weeks ago where we are aiming to collaborate with industry companies and universities in Europe, especially around 5G and using 5G for this new type of use cases. Because we think that in order to have a successful system design and a successful adoption of 5G for these industries, we need to involve the industries early on. And the way to do that is not necessarily through standardization, but we need to engage in doing different piloting and trials and so on with these industry companies that may not be so aware of what 5G can provide and what the capabilities are and so on, because they are used to other type of technologies. So therefore we have launched this 5G for Europe recently. We have announced the first set of partners here. We have King's College is there, right, and Tampere University will be there as well. And we are sort of adding now different, both on the university side and on the company sides, partners into this collaboration. So this we think will be very important to capture all the relevant industry requirements into the 5G design. So hope to see some of your universities there in the future also. Okay, that leads me to the summary, and on this picture here you see our first 5G mobile that you will be able to see if you visit Kista. It's a bit big, but it's actually smaller than the first 4G and 3G mobile. So this is how they look in the beginning. Yeah, so we think that we really foresee that 5G will cover much more than just mobile broadband and media. And I think this will be the major new thing with 5G compared to what you have today. And I think we will see new business models. I think that is really needed in order to address these industrial use cases. We also see that the LTE will play an important role here, and we will see many of these, what we now call 5G use cases, will be adopted gradually also into the LTE evolution. Maybe not all, but many of them. And we have a phased standardization in order to ensure that we have an early commercial launch, as well as we can sort of include all the necessary functionality that we need to be fully 5G compliant according to ITU. And then we need collaboration, both with the universities and industry players to really make this happen for the industrial use cases. If it was only about mobile broadband, I think the telecom industry could have done it themselves, but now this is a bit different. Yes, that was my last slide.
Thank you so much, Johan. Any questions to our keynote speaker? So in that part, please prepare.
Thank you for your presentation. You mentioned a successful test with driving the vehicle remotely. You also mentioned something about factory automation. What is the maximum number of devices that were connected together before deadlines were missed, so absolute breakdown utilization? In case of factory automation.
I mean, how many devices that can be connected?
Yeah, together before you start missing deadlines.
Okay, until you can, yeah, okay. So how many devices can you support in a factory automation scenario before you exceed the latency bound? I mean, that depends, of course, how critical the application is, so what latency bound do you really need and how much bandwidth do you have available and so on. So I think in a factory, maybe the factory is actually not the first scenario where this will be used, but it's sort of an extreme example. That's why we like to talk about it, because it has some extreme requirements. But it's also a sort of quite confined environment where you have some control of your interference situation also. So I think it's relatively easy to actually support many critical MTC devices in that scenario. It will be more difficult if you would have them in the middle of the city or so, with a lot of other traffic as well. But I don't have any exact numbers. We have some papers on that if you want to see. But,
Thank you.
Johan, thank you very much for a very insightful presentation. I may also have a very good question on the bit that you kind of mentioned in the release 14 puzzle, but you kind of skipped very briefly. That's LNA. And what's your personal take on that? Because I think it's more dangerous than people might think, right? Going for LTE going to unlicensed spectrum, that's threatening Wi-Fi community, right? And then there's a fairness of using a semi-scheduled versus, unscheduled access. So what's your personal take on that? And it's a big thing, right?
Yeah. So LLA. So for those of you that are not aware of that, I mean, that's then about using LTE in the Wi-Fi band. It has caused a lot of discussion from the Wi-Fi community because, I mean, this is sort of they see it as a threat, a new technology coming into their bands, even if it's an unlicensed band, right? And I think I can partly see their concern, but from a technical perspective, I'm not so worried. I think we will make sure in the design that we are sort of a friendly neighbor, if you like. So if you have one LTE network in the building, one Wi-Fi network in the building, and if you then deploy this LLA, that should not cause any more interference than if you would deploy another Wi-Fi system as a neighbor. So we should.
Sounds very vague. It's like, how would you measure that? What would have existed if you are not there?
Yeah, I mean, I of course, you would need to define exactly how you measure it. But for sure, we don't want to. I mean, you could design a system that is aggressive, right, and sort of consumes all the resources by being slightly faster than Wi-Fi and grab the channel slightly faster and so on. But we will not do that. So we will make sure that they can coexist.
Yeah, I think the key question there is how to define fairness between the scheduled and an unscheduled system, and that's what causes many discussions, or at least to what I'm aware.
How you define fairness? Yeah.
Yeah, but that's definitely
we can define it over lunch. That's it.
Thank you. Any other questions? All right, so then my personal question also about the integration with existing technologies. In particular, I'm interested in this automotive case with platooning. So we know about the SRC.
Yes.
As a technology that considered to be, the automotive technology. So, from other hand, we have these 5G developments towards coverage of that scenario as well.
Yes.
So, what's the proper path in that in the implementation? Will it be a joint LTE DSRC, or why LTE should be able to cover the scenarios versus the technology that is designed specifically for automotive? So what would be your personal opinion on that? And
So I think that's a tricky question, and we don't know exactly how this will develop. Right. On one hand, there are some regulatory. Or there might be regulatory requirements that the sort of this 11 Wi-Fi based solution should be mandated in the US.
DSRC as the technology to go.
So that may happen. At the same time, we think that cellular connectivity will be in place in all cars, both for this e-call that will be mandated, and also to support different infotainment applications within the cars and so on. So the cellular communication will be there, and then sort of there's a question of how can you combine these in a good way, and exactly how that will happen, I don't know. I mean, it could be so that this 11P based technology is used between cards, but when you communicate with the infrastructure, you use LTE. That could be one scenario, but exactly how it will play out, I don't know. But our ambition is that the LTE should be at least as good as 11P also for device-to-device communication. So it should have that capability.
Good to know. All right. Anybody else, or we just thank you, Johan, so much for your talk, being with us.
Okay.